Hello class. For week 4, we're going to continue some more discussion about sets and then specifically numbers and numeration systems, including base 10 and other base kinds of counting. Let's begin with item number 1 here from our guided notes. Consider the set of all U.S. cities. There are two basic ways to express this. Let me write down the two ways. One is, I call this the lazy way of describing a set. Let's say A stands for this set, and you just put curly brackets and then put the elements of the set. Now there's too many to list, so just putting a description here is fine. Something like all U.S. cities. Now there's also a more formal way to express a set called set builder notation, and it looks something like this. You say A is equal to the set of all, and then put a variable here. Often you'll see an X, or it really doesn't matter what letter, of all X, and then you do a vertical line which stands for such that X is a U.S. city. And then you close the set notation. This is the more formal way to describe the set of all U.S. cities. Again, let's read it from left to right. A is the set of all things X such that X is a U.S. city. This becomes a helpful way for describing sets down the road when we start dealing more with mathematical sets of numbers. Okay, let's go to item 2 next. In the last unit, we discussed unions, intersections, and complements of sets. Another set operation is called the set difference. Consider the following sets written using lazy notation, not set builder notation. The set difference is defined to be, let me do first a symbol for it. For example, if I were to do A and then a minus sign and then B. This is defined to be the set of all things that are in A but not in B. Right, where a union, let's do a little Venn diagram here. Let's pretend our A and B intersect this way. Now in this case that's not the case, but let's just pretend. So we have A and B. The union, I would shade in everything in either one of these. That would be the union. The intersection, we would only shade what's common. The complement of A, if you remember, there's going to be some greater universe in which these sets reside, and the complement of A stands for everything that's not A. Right? So you would be everything in the universe that's not in A. We'd call that the complement of A. Now, when I say A minus B, I'm saying everything that's in A that's not in B. So it winds up being, you shade everything that's in A, but it can't be in B. So you wind up shading just this portion here, and this would be A intersect B. So not A intersect, A minus B. Sometimes instead of, let's look back over here again right there. Sometimes instead of a minus sign, you see more of a slash like this. And this also is considered the set of A minus B. Everything that's in A, but that's not in B. Now let's consider a few other considerations of how A and B, let's get rid of the universe, how A and B might interact with each other. What if they're disjoint? And I say, hey, what's their intersect, or their union? Their union would, whoops, wrong thing. Their union would just be everything in one and or in the other. Their intersection would be the empty set. There would be nothing that's in both. And if I say, hey, what's A minus B? Then you say everything that's in A that's also not in B. Well, everything in A is already not in B. So in the case of where A and B are disjoint, A minus B would just be A again, if that were the case. And another possibility is that B, let me go ahead and erase the B there, but let's say that B is, I'll make it a little bit smaller. B is entirely contained in A, something like this. Oops. Let's make that even smaller. So let's say that's the set B. B is a subset of A. And I asked you to do A minus B. Well, it'd have to be, you would shade in everything that's in A, but not in B. It's going to be hard to shade, but you get the idea. I would have to do a, move that more middle. This would be easier to draw, or change how thick this pen is, but there I'm shading everything that's in A that's not in B. And that's how you would interpret that if B was a subset of A. What if A was a subset of B? What if this is A and this is B? And I say A minus B. Here you would have to shade everything that's in A but not in B. But everything that's in A is in B, so there's nothing to shade. This would give us an empty set if this were the case that A was a subset of B. But now let's look more specifically at this context here where A and B represent these particular sets. A is a set of all cities in the US, B is all cities in Arizona. So in this is a case where we would have, right, A would be a larger set and B would be a subset, because every single city in Arizona is also in the United States. So when I say, hey, what's A minus B, you're going to wind up shading everything that's in A but not in B. In other words, it's all cities that are not in Arizona but are in the United States. If I were to use set builder notation, we would say it this way. This is equal to the set of all x such that x is a US city not in Arizona. And this is what A minus B would be. How about A minus C? All cities in the US minus all world cities that begin with the letter P. Okay, so we have cities like Phoenix, that's in the United States, and plenty of other cities. And you have the French city Paris, or other cities like Prague that are outside of the United States. And so in a case of A and C, here's all the cities. This is A, all the cities in the US, and all the cities in the world that begin with the letter P would be something like this. This would be set C. So when I say do A minus C, you want to do everything that's in A that's not in C. In other words, you want to do all US cities that do not begin with the letter P. So in set builder notation, it would be, let's use a different letter here, all, I don't pick a letter, all G, such that G is a US city that does not start with P. Does not begin with the letter P. Okay, let's do all the B's. Let's do B minus A. All cities in Arizona minus all cities in the US. Well, all cities in Arizona are also in the US, so this is a case, right, where B is a subset of A. And if I do all cities in Arizona minus all cities in the US, then there's nothing that's in B that's not in A. So this is the empty set. B minus C. All cities in Arizona minus all cities in the world. Well, there are some cities in Arizona that start with P, and there are some cities in Arizona that do not. And so we have a relationship between B and C like this. And so when I say B minus C, I want to shade in everything that's in B but not in C. So you're going to wind up shading in something like this. So using set builder notation, this would be, let's use Y instead, all Y. So you have to be in B but not in C. So this would be all AZ cities, but we removed every single world city that begins with P. So we have to remove all the Phoenix cities that begin with P. All Arizona cities that don't begin with P. Let's do the other subtractions. C minus A. Start with all world cities that begin with P and remove all US cities. So this would be set of all X such that, oh, I forgot. I did a bad notation here. I went kind of lazy combined with a set builder. I should have had a Y right here right away. Y is a Z city that, instead of doesn't begin with P. That's better. So anyway, back to C minus A. C minus A is X is, so we want to do all cities in the world that begin with P, but none of them could be in Arizona. So X is a non-Arizona world city begins with P. I'm being a little bit lazy in my writing to go quickly here, but C minus A. So everything that's a world city that begins with P, but you have to remove from that all those cities that happen to be in Arizona. Why am I saying Arizona here? I do not know. I was thinking C minus B, even though I wrote C minus A. C minus B is all non-Arizona world cities that begin with P. C minus A, let's go with a little b, such that B is a non-US world city. Again, begins with P. There. Good enough. So those are all the different possible differences you could do given these three sets. Now let's do a little exercise. We have a Venn diagram. Oops, didn't mean to zoom in. We have a Venn diagram here. We're going to give two different ways to express each colored portion. Now there's a blue, a green, and a yellow portion. Let's start with the blue. And let's give these sets some letters. Let's say we have set A is on the left and set B is on the right. So the blue portion, if I only want the blue portion, again, that's just this crescent moon right here, that's it. We're not saying all of this, right? That would just be A. But I want to describe just the blue. And the blue portion, one easy way to do it is to say, hey, everything that's in A that's not in B. And that gives you that blue crescent moon. So the subtraction is a nice quick way to describe such a set. Another way you could describe the blue portion is to say anything that's in A and intersect it with anything that's not in B. Right? Because if I say anything that's in A, I'm looking at this. Okay, that's shaded everything in A. Now shade everything that's not in B, but still in the universe, right? You see where I'm going with this. I'm shading everything not in B. And the question is, what did I shade twice? Well, the crescent moon right here got shaded twice. So that's an intersection. We did everything that's in A and not in B. So yeah, a second way we could have done this was to say, do A and intersect it with the complement of B. Remember, put a little C there is one way to say complement. Put a little prime sign there is another way to say complement. Or put a bar above the B, that's another way to say the complement. For the yellow, let's do that one next. Yellow is everything that's in B but not in A. So if I just do B minus A, that'll work. Describe the yellow. Another is to intersect everything that's in B and intersect it with everything that's not in A. Right? Because anything that's in B but not in A and not in A would be in that yellow portion. And now let's do the green. The green portion, the obvious way to describe the green portion is just intersect A and B. So A intersect B is what gives you green, right? In fact, that's what really happened when you mix blue and yellow, you got the green. So the green was what was shaded twice, essentially, once by the blue, once by the yellow. It made that green middle portion, which is the intersection. Let's see if we can come up with a different way to shade the intersection. maybe do a some sort of subtraction. And there's probably lots of ways to do this. Let's just see if we can come up with one way, maybe using the subtraction. What if I started with everything that was in A? There we go. And from that, I want to remove everything that's not in B. Right? So if it's not in B, so we're starting with everything that's in A, right? When we do subtraction, to start with everything that's in A, and then what are we going to remove from that? What I want to remove is, all right, so let me do this again. I'm starting with everything in A, so this is what I'm focusing on. I want to remove this crescent moon over here. Well, what's true about the stuff that's in that crescent moon is that it's not in B. So if I do A minus B complement, start with everything in A and remove everything that's in A but not in B, and then I wind up with everything that's in A and B. So there's just another way there to describe an intersection. Okay, let's go on to the next item, item 3. The cardinality of a set is the number of elements that the set contains. Very simple idea. Consider the following sets. To indicate that we're doing a cardinality, there's a few ways to do this. I've seen some people put the set in absolute value bars like this, which says what's the size of the set, which just means how many elements are there. There's 1, 2, 3, 4. So you would say the cardinality is 4. Also, you see this notation where you put an n in front of some parentheses and the set A in there. This just kind of means the number of elements of the set A. It just means what is its cardinality. And there's 4 elements in there. I'm going to use this number one for the rest of these, number notation. Look at the set B. The set B actually has a duplicate element. And so that can be deceiving. The elements of a set should be distinct things. And so it's really best to just write set B this way and not, have any repeat elements in there. And so the cardinality of B is actually only 3. There's 3 different elements in there. C is a set of all cities in Arizona. I don't know how many cities there are in Arizona. We could look it up. Let's just say it's some number. We'll just say it's some finite number, right? Because there's only so many cities. When I say finite, I mean the opposite of infinite. Some finite number. Maybe someone can look it up. Let's say do some research. So it's not always easy to know what the cardinality of a set is. And sometimes it's really not possible to know. Even it could be finite. For example, if I say let n be, or let C be the set of all people who are currently alive right now on the planet. No one really knows that number. And as soon as you try to go about trying to find that number, people are dying, people are being born. It's really a moving target. But it's certainly there is a number at any moment. We just don't know what it is. But it would also certainly be finite. And then D is a set of all possible numbers. Well, if I just start writing possible numbers, this list would never end. You could even throw, fractions or other kinds of numbers in there. There's really infinitely many numbers. The list never ends. So you would say the cardinality of D is infinity. And for you to say, do some research to find out. We could probably answer the question about how many cities there are in Arizona. That one is likely answerable, even though a city might be born. How often are cities born in a state? Probably not very often. But all people on the planet would be probably an impossible number to accurately determine. Okay, let's look at some other nuanced things here. 2 sets are equal if they contain the same elements. The order does not matter, right? So if I have a set that has the elements A, B, C, and then a second set that's presented has the elements C, A, B, you would say that these are equal. Now, the order doesn't matter when you're talking about sets. However, 2 sets are equivalent, this is different, if they have the same cardinality. There is a funny case with infinity. So let's go with a for the sake of this class, let's just talk about finite cardinality and equivalence. It gets pretty deep when you start talking about whether infinities are equal or not, something beyond the scope of this class. So let's just go with finite cardinalities for equivalence. So if you had a set A is equal to, again, A, B, C, and a set B was something unrelated to A, B, C, like 1, 2, and then a star, right? Doesn't really matter what they are. It doesn't matter that the elements are the same or not. They both have cardinality 3. In such a case, it's possible to establish some sort of one-to-one correspondence between the elements of the two sets. So I could correspond A with 1, and they don't have to. I could correspond the B with the star and correspond the C with the 2. Right? There's variety, but for every one element in A, you could match it with an element of B, and then everyone would have a partner, so to speak. There's a one-to-one correspondence with these two sets. And the symbol that we do when two sets are equivalent, we say A corresponds to B. Whereas up here, we would say A is equal to the set B. Now, trivially, if two sets are equal, then you could also say that they're equivalent, right? Because they have the same cardinality if they're equal. Another thing to conclude that two sets are equal is if A is a subset of B, you must have the partial equal sign on here. Otherwise, this wouldn't be true. And B is a subset of A. If both these statements are true, then that's another way that also implies that the two sets are equal. Okay, let's go on to item 5. An ordered pair is a collection of two elements, the order of which is significant. So normally ordered pairs are put in a set of parentheses, and you've probably done this before in math, like 3, 2 is a point. It's an ordered pair. It's not the same thing as 2, 3, right? That's what I mean when I say the order is significant. These are considered different ordered pairs. But they don't have to be numbers either. You could have letter A star. This would be an ordered pair, right? They have to be some element. You could have, Phoenix. A U.S. city is one element, and then a cow is the second element, right? This would still be considered an ordered pair. Collection of two elements, the order of which is significant. So it's not saying the same thing as a set of two elements, because when you say a set of two elements, and I put it in curly brackets like this, A star, as far as sets are concerned, this is the same set as star A. Right? So order doesn't matter when we're talking about sets, but order matters when you're talking about ordered pairs. That's why we're considering these two as two different ordered pairs, even though those two would be considered the same set. A Cartesian product is a set of ordered pairs created from two sets as follows. Okay, so let's say we have two sets. Let's say A is a set of numbers 1 and 2 and 3. And B is a set of letters, just A and B. A cross product, a Cartesian product, is when you do A cross B. And what it does is it makes the following. I'm going to use set builder notation. Well, I'll do set builder notation after. I'm just going to start writing some of the elements of this new set. So you take two sets, A and B. They could be the same, they could be different, they could be disjoint, they could have a non-empty intersection, meaning that they overlap. They could be whatever sets you want, it doesn't matter. A cross B is a set of ordered pairs. So every single element of this new set is going to be an ordered pair. So there's going to be an ordered pair, etc. Maybe a whole bunch of ordered pairs. We'll figure out how many there are in just a moment. It's a set of ordered pairs. Created from the two sets as follows. Okay, so the first element of the ordered pair has to be something from the set A, and the second element has to be something from the set B. And we just do all possible combinations of that. So for example, I could do 1 is the first element that comes from the set A, comma, and then little a comes from the set capital B. Maybe let's use more numbers, just so I don't have to say little a and big A and all that, and it gets confusing. So let's do 1 from set A and then 4 from set B. But we could also do 1 from set A and 5 from set B. And then we've exhausted all the different ways I could use a 1 in the first position. Next one would be we'll use a 2 in the first position, and we get 4 as a second possibility, or we could do 2 comma 5 as another possibility, or we've now exhausted all the different ordered pairs that have a 2 as the first position, and now we're going to do a 3 in the first position because 3 also comes from set A, and then 4 or 5 could be the second position. So this would be the set, the Cartesian product of these two sets, A and B. Set of all ordered pairs where the first element is something from A and the second element is something from B, and we do all possible combinations. The way you would write this in set builder notation is the following. So you would say the set A cross B is the set of all points x comma y, or all ordered pairs x comma y, such that, that's what that bar means, such that x is an element of A and y is an element of B. And here's a formal way using set builder notation to describe a Cartesian product. This is a good, Cartesian products are good where you're trying to describe all outcomes of two events. For example, let's say that you draw a number from a hat and the options are 1, 2, and 3, and then you draw a number from another hat and the options are 4 and 5, and the question is, what are all the possible different outcomes you could have? And that's what the Cartesian product reveals when you talk about the outcomes of one draw followed by a second draw. Something like that. Okay, item number 6. The natural numbers, also known as the counting numbers, are as follows. It's a set of numbers, the smallest of which is 1. And then these are all the counting numbers. So I'll just go in order, 2, 3, 4, 5, 6, and forever. There's infinitely many numbers in this list, and the way the letter that is used often to represent the set of natural numbers is a bold capital N. Usually is what's used to represent the set of all natural numbers. Or if you can't write bold and don't want to do what I did, sometimes you just see an N with a double bar on the left side of it like that. And it stands for the natural numbers. Oh, by the way, up here, as far as Cartesian products are concerned, if you wanted, the cardinality of A is 3 and the cardinality of B is 2, can you guess what the cardinality of the Cartesian product is going to be? Well, we can actually look at it. How many ordered pairs are in this? Don't count elements, count ordered pairs. And there are 6 ordered pairs in there. And 6 is the product of 3 and 2. All right, that's always going to be the case with the multiplication principle. It's also like, let's say A is a set of, you have 3 pairs of pants, right? There's another example. You have 3 pairs of pants and 2 shirts. And I say, how many outfits can you have? Which includes a pair of pants combined with a shirt. And there would be, 6 different outfits you could possibly wear. So you can see in practical day-to-day living, Cartesian products are relevant things. And if I were to say, hey, what's the cardinality of the natural numbers, right? The number of natural numbers is clearly infinity. It's an infinite cardinality. The whole numbers are the same as the natural numbers, except that 0 is added to the list. And typically a bold W, as you might have guessed, is used to represent the whole numbers. So 0, 1, 2, etc. There's infinitely many of these as well. Sometimes if you don't want to do a bold W, you can just do a W that has a double bar on the left like that. And this would be good enough. Some relationships between these two, right? If you were to take the natural numbers and do a union with the element 0, right? So anything that's a natural number or 0, this would form the set of whole numbers. If I took the whole numbers and I subtracted the element 0, right, removed element 0 from it, then that would give you the set of natural numbers. Also, there's a relationship between these two. Since every natural number is also a whole number, then we know that one of these is a subset of the other, and it goes this direction. In fact, it's a proper subset, so I could say this without... It's also technically true if I put this bar here as well, because that allows for the possibility of being equal, but we know that they're not equal, so it's more information to leave that off and say that n is a subset of W. Right, if you're doing a Venn diagram, what that means is, you would have the n circle contained inside the W circle. In fact, the only element that's would be in this ring would be 0. 0 would be the only element there, and all the other numbers, 1, 2, 3, etc., would be in that inner ring as well. So a little Venn diagram there as well. Let's erase that dot. Put dot, dot, dot. Okay. The whole numbers can be positioned on a number line to establish order and relative positioning. You've done this before. You can just make a number line, make it increase one direction, often to the right, although technically you could point this any direction you want. But normally this is the convention. We'll start at 0, and then we do even spaced hash marks, right, to represent all the different counting numbers. And we create a number line. Now, in general, when you're comparing numbers that are further to the right are considered to be larger than numbers that are to the left, right? So if you were to take 2 and 5, you would say a statement like this. And remember this symbol here, you would say 2 is less than 5. Think of this as like an alligator mouth that's trying to eat the larger number, so it should be opening up towards that 5. You could even say, if you picked of course, you could say this the other way around too, right? You could say put the 5 first, and 5 is bigger than 2, so these are communicating the same thing. Technically, you could also get away with this, right? Because it is true that 2 is less than or equal to 5. It happens to be the less than part. So technically, you could also say this. But, of these 4 options here, the ones that are most informative are these ones. But technically, these 2 statements are true as well. If you compared 3 and 3, technically you could say, this is technically a true statement because 3 is less than or equal to 3. It's better to say this though. That's more informative. This one, is not as conclusive as a statement as this one is, but technically both of these statements are technically true as well. All right, item 7. The numeration system that is widely used today, and the one you are certainly already familiar with, is the base 10 numeration system, also known as the Hindu-Arabic numeration system, because both those cultures contributed to its development, or the decimal numeration system. Decimal means desa refers to 10. Right? So this is base 10. Consider the number 273, or just 273. Explain the meaning of each digit. Right, so the positioning of these digits matter. Like this is not a 2, a 3, and a 7, some that are combined together, right? Because if you just combine 2, 3, and 7, you would get a total of 12, which is not what this is trying to communicate. So the 2 doesn't really mean a 2, and the 3 doesn't really mean a 3. Does the 7 really mean a 7? That's a good question. Let's try to make sure we can say this clearly, what's going on here. When your third number from the left, this tells you how many hundreds there are. So this really means you have 200, not just 2. When your second number, did I say from the left? Or to the third number to the left, second number to the left, or we'll say third number from the right, second number from the right, first number from the right. The 3 is in a position that's called the tens position, and it really means that there's a 30 there, and then the 7's in the ones position, meaning that there's just 7 ones. And so when you see a 2, 3, and a 7 written together like that, it really means you're combining 200, 30, and 7, not 2, 3, and 7. So this is a different thing to think about than combining 2, 3, and 7. Now I'm going to show you a few different ways that this can be modeled, especially for maybe for your own development, but also as you're helping children develop their own understanding of our number system. Express 237 as a combination of hundreds, tens, and ones. So we're going to say how many hundreds do we want, and add that to how many tens do we want, and then add that to how many ones do I want. Well, the 200 means you have literally 2 100s. The 30, when you spell it out, 30 is short, or T is for 10, and 30 is the beginning of 3, related to 3, so this means 3 tens. 20 means 2 tens. 70 means 7 tens, etc. You get the idea? So 30 is 3 tens, and 7 just is 7 ones. So we have 2 hundreds, 3 tens, and 7 ones put together, and that gives us this number that we call 237. You can also view these as different powers of 10. For example, we'll start with ones as our base. Then we have 10 times that number 1, and then 10 times 10, in other words 10 squared, is another way to think of the 100. And you have powers of 10. You could think of this 10 here as a it could be a 10 to the first there, if you want to think of it that way. And you could think of this 1 here as a 10 to the 0. Let me put that in red. 10 to the 0 is the same thing as 1. So you really just see you're counting powers of 10, right? There's 7 10 to the zeros, 7 10 to the first, or sorry, 3 10 to the firsts, and 2 10 squares. We're going to do something very similar using a place value table to represent. I'm going to do a bunch of dots in here instead of actual numerals. The first box here on the far right will be the ones position. Then we're going to have the tens position. Then the 10 squares, or the 100. Right, you can do 10 squared or 100. This would be the 1,000 position, or 10 cubed, etc. And then we could do more boxes as necessary over here, depending on how big of a number. In fact, for this particular number, we're not even going to use this box here, but use as many boxes as necessary, working this direction from right to left. And I'm going to use dots in the box. So this 7 ones, I'm going to put 7 dots in there. So there's your 7 ones. Now a dot in this box means you're counting tens. So the 30 would be, you put 3 dots in here, and that represents 3 tens. And in the next one you'd put 2 dots because there are 2 hundreds. Now sometimes you'll just put numerals in here, like you put a 2 in there, a 3 in here, and a 7 in there. But we have this idea that 237 means really 2 hundreds, 3 tens, and 7 ones all combined. Now let's pretend that I'm going to give you a little precursor of something that's going to happen down the road. Let's say I added 4 to this number. That's like putting 4 more ones in this box here. But a phenomenon happens that every time you get, you can highlight them, there you go, count those dots right there. There's 10 of them. Right? I just circled 6 black dots and 4 red dots that I just added. And those would disappear and resurface. Let me just delete them. And they would resurface in here as a new dot. Right? So if I started with 237 and I added the 4 dots into the ones box right here, the new result is going to be, we have 2 hundreds here, We've now 4 10s and only 1 left, right? So we just sort of showed visually that 237, add 4 to that, we get 241. What's happening here is the same idea that you learned when you add 7 and 4, you get 11, you carry the 1, and then you add those and you get the 4. Really, you're adding 10 to 40, not 1 to 4 is technically what's happening here. I don't know, just go away. And we'll talk more about that algorithm later. But the idea here is that the reason I'm showing you this ahead of time is that you never, in any one box, you can never have more than 9 dots. Right? So look at this one right here. Currently there are 7. I could put an 8th and a 9th, but as soon as I do a 10th, then all of these would move over, would collapse, delete, and result in a 1 new dot appearing in the 10th, in the tens position, leaving, you know, nothing left in the ones in that case. There we go. So no box should ever have more than 9 dots in it. It could have no dots in it or up to 9 dots. So there's 10 options there, you know, counting the 0. The 0 through 9 gives you 10 numbers. You know, if I added 8 more dots to this region, then we would have a 10 of those dots would combine and form a single dot in the next box over type of idea. There's a mathematician who likes to call these exploding dots. When you get too many dots in a box, they explode and they reemerge as a single dot in the box to the left. And I'll put a link to a video where he explains this exploding dot phenomenon. He's a fun guy, lots of energy. I think you'll enjoy the video. It's not very long, but I'll put it also in our Canvas week 4 page, so you can watch that. Another way to represent the value of 237 is by using these base 10 blocks. Now your notes have just a picture of the basic base 10 blocks. So you have a single box down there that represents 1, then you have 10 in a row, and then you have 10 by 10 that represents the 100, you have 10 by 10 by 10, this represents 1,000. So you see these blocks form visual, quantitative enforced visuals for how big these numbers actually are. And working with base 10 blocks, if we wanted to represent 237, right, I copied these images here into this. If I have 2 hundreds, so the hundreds are the orange, so I need another one of these. Right, put them next to each other. So there's my 2 hundreds. Then we have 3 tens. The 3 in the 10 position means 3 tens, so let's copy this one. Paste. And let's paste another. There it is. Let's move that guy out of the way a little bit. So sometimes these are stacked. Doesn't really matter how you stack them. Anyway, there's 3 tens. And then we want 7 ones. So we're going to paste a bunch of these until I have 7 of them. And what are we at? 6? Okay, one more. Whoops, that's not what I wanted to do. Drag it over. Okay, you can stack them in a cleaner order, but here you can definitely see we have 2 hundreds plus, and we're combining 3 tens, and we're combining that with 7 ones, right, to represent this 237 value. Right, if there were a number in front of the 237, like a 5237, then we would need 5 of these 1,000 blocks to help represent that number as well. If we were not doing this class remote and sitting in a classroom all together, we would actually have these manipulatives to work with, these blocks, but you're going to have to imagine working with them for this purposes of this online class. Okay, what are the only possible digits in a base 10 number? Right? That's related to what I said up here about how many different dots you could allow to exist in a box before they exploded and became a single dot in the box to the left of it. And that is, once you get to 10, right, 10 dots in any one box, they will collapse into one dot in the box to the left of it. And so the only possible digits in a base 10 number are 0 through 9, essentially. I won't write them all, but that's a list of 10 options. Right, you either have no dots in a box, like we have no dots in this box, or you have up to 9. Because once you have more than 9, then you would have an explosion of the dots. They would collapse into a single dot into the box on the left of it. And that could create a ripple effect, right? If there were already, let's say there were already 9 dots in this box and you had 10 in this box, then they would collapse and form another one here, which would make that 10, and that would collapse and form another one here, right? So there could be this sort of ripple effect of, oops, that's ugly, yeah, ripple effect of explosion of dots. Collapsing 10 dots into one could have this ripple effect. Okay, let's talk about other bases other than base 10. Now these ones you're probably not as familiar with. We're going to talk about base 2, which is actually what's called binary. So people who work with computers, computers read ones and zeros and interpret them as numbers. Also, some computers use this hexadecimal, which is a base 16. We'll have to talk about that in a moment. Let's do the base 10 number 237, and we're going to actually write this in binary, a base 2 system. Now the base 2 system, what does this even mean? What I'm going to duplicate is this idea right here in this table, but we're going to have base 2, meaning that if there are ever 2 dots in one box, those 2 dots will combine and form a single dot into the box to the left of it. So let's begin by making a table, and then breaking this up into these boxes, something like this. I don't know how many I'll need, so I just do a whole bunch of them, see how we go. So this is the 1's position. The next one is the 2's position. Now up here in base 10, remember this was like 10 to the 0, which is just 1. This is like 10 to the 1, 10 squared, 10 cubed, etc. And the base is 10. That's why we call this base 10. Remember, when you have an exponent situation like this, that this part's called the base and that part's called the exponent. So we have base 10 going on here with the base 10 system. With a base 2 system, we have a 2 to the 0, which is essentially 1. We have a 2 to the first, which is 2, a 2 squared, a 2 cubed, and notice I'm just doubling as I go. And one more box would be, let me just put it in there for just a moment, 256. So I just doubled and doubled and doubled. Now, the way you want to do this, if I put a single dot in here in the 1 box and stop there, then when you write this out, you would have 0, 0, all these boxes. You could have as many zeros in front as you want, but 0, 0, 0, 1 was what this would be when you write this in binary. It stands for you just have 1 unit, something that's equal to 1. As soon as I put 2 dots in here, though, they will merge, move over here, and become a single dot. Right? So in other words, 2 dots in the 1's box equals 2, but we have a box for 2's. So we just have to put a single dot in the 2 box, and that means we have 2. There we go, get rid of that circle. If I ever were to have a second dot emerge in this box, that would be 2 2's, and whenever all pairings in any box would move over to the next box and become a single, right? 2 2's makes 4. If ever I had 2 dots in this box, right, 2 4's make 8, so they would just merge, go over here and become 1. You get the idea. So I can never have, I can't make this number 237 by doing a whole bunch of dots in the 2 box until I get there, right? There'd be lots of them. and say, there we go, that represents 237, because all these different pairs would become a dot over here, another pair. And once I had two dots in here, there'd be a ripple effect. It'd make a dot over here. And eventually there'd be another dot in here, and then those would collapse and become a dot here. And all sorts of chaos would ensue. The best way to do this, to figure out where the dot should be to help me get this number, is to do the following. Go down the list until you get to a number that is more than 237. So this 256. And we don't want any dots in here, 0 dots in here, because if I had a single dot in that box, that would mean we had 256, but I don't. So we actually don't need this box over here at all. Also, there can be at most 1 dot per box. So there's either no dots or 1 dot. So we definitely need a copy of 128. And let's keep track of where we're at by when I add these things together. Do I need any 64s? Well, if I add 64 to this, the question is, will that put me higher than 237, or am I still less than it? If I'm still less than it, then I want definitely a 64 present. Well, let's add these together. 128 plus 64 is 192, and that's still less than 237. So we need a 64. The question is, now do I need a 32? Let's add 32 to this. That gives me 224. That's still less than 237, so we need a 32 involved. Do I need any 16s? Well, if I add a 16 to this, this will take me to 240. Well, that's more than 237, so I don't need any 16s. So we skip the 16 box. We go to the 8 box. Add 8 to 224. That gives me 232. That's still less than 237, so we can have an 8 present. How about a 4? Can I now add a 4 to this? If I add 4 to this number here, then we get 236. Right, so that's okay, that's still less than that. So I want to make sure there's a 4 represented. How about 2? If I add 2 to this number here, that goes too high. So we don't want any 2s, but we do want a 1. Because adding 1 will take us to that 237. Let me move this work over here. Okay, so there is our binary number. We go as far this way as we can to find our first dot. If there's more boxes over here that have no dots in them, then you don't need to bother putting zeros in your binary number, just like in the number 237, right? Or just like in base 10, I don't need to put zeros here, although I could. No, this is still 237. We just want to go as far over until we have a non-zero entry. So I don't care about boxes over here that have zeros. The first non-zero entry is right here, and there's 128. Then there's 164. Then there's 132. We have no 16s. We have 1 8, 1 4, no 2s, and 1 1. So in binary, let me actually make this smaller too, so I have some space to do some things. In binary, the number 237 is represented by the number 111011101. That gives us 237. Computers can see that and recognize that very quickly. So we're saying the following, that 237 is the same number as 111011101. If you look at this but think that we're in base 10, then this is a crazy number, 11,101,101. You're like, wait, that's not the same thing as 237. But you can't look at it the same way. A way to tell which base we're using is to put a little subscript down here that says base 10. When you start doing with other bases, then you need to specify what base this number is representing or is being used. And this would be base 2. Or sometimes you'll just put the, instead of spelling it out, put a little base 10 there and a 111011101 base 2. This is communicating that this is measured in base 10. So the base that we're already familiar with, we already have a good sense for 237. And this is that same number, but in base 2. Let's see, what else can I say? Oh yeah, when you're in binary, when you're in base 2, all your digits should be 0s or 1s. Right? There should be 2 options for every digit when you're in base 2. Just like there were 10 options, right? Look at this work. When there are 10 options for each digit when you're in base 10. Right? This is a consistent pattern. The number of options per digit is equal to the base that you're counting in. Let's do a base 6. And for that, I'm going to largely, copy most of this. Paste here. We're in base 6, so let me get rid of these. Get rid of the dots and get rid of our binary. Get rid of all these dots. Okay. I'm not sure how many boxes I'm going to need, so let's just see. If I don't use them all, so be it. So the last box to the right is the 1s. Now we're in base 6. So this 1 is like 6 to the 0. The next box should be how many 6s we have. Then 6 times 6 is 36. 36 times 6 is 216. And 6 times that, oh boy, 6 times 16. We have 6 6s, that's 36. We have 6 10s, that's 60. And 6 200s, that's 1200. Add those together, we get 1296. So 1296 is the same thing as 6 to the 4th. And I really don't need any boxes past that. Right, so let's just go. Let's stop our. Oops. Let's stop our box at our table at that box. Right, and just for the sake of notes, remember this is the 6 to the 0s, the 6 to the 1s, the 6 squares, the 6 cubes, and the 6 to the 4th. Now the reason I stopped there is because we've now gone larger than this 237 that we're trying to add up to. Okay, so I definitely don't need any of these. I don't need any 1296s, because that's already more than 237. How many of these do I need? 216s. I'm not sure what's happening here. Here we go. I definitely need one 216. Do I need more? No, 2 216s is too much. Remember, in each of these boxes, you can have up to 5. Right? It's only when you get a 6th that these group of 6 will merge into a single dot over here, right? So we can have up to 5 dots per box. But in the first, I only need one of the dots. I only need one dot in this box here, because 216 gets us close to 237. Let's move this over and put my work over here. So I have one copy. I'll write this. We have one copy of 216. That's 216. And we want to see what we have left to create. So I'm going to do 237 minus 216 and see what's left. When I subtract these, I get 21. So I have to account for 21 more. Well, 36 is too big. I don't need any 36s. So no dots in the 36. However, how many 6s can how many 6s are required to get me as close to 21 as possible? Well, 3 6s will give me 18. So I'm going to put 3 dots here, right, because 3 6s gives me 18. And let's do this 21 minus 18. That gives me, I have 3 left to deal with. And I can do all 3 of those singles here in the 1s position. So these dots literally mean that we're doing, we have 1 dot here, so we have 1 copy of 6 cubed, plus, and we don't have any 6 squares, but we have 3 copies of 6 to the 1st, or just 6, and we have 3 copies of 1. What we just figured out is how to use powers of 6 to create 237. So 216 plus 18 plus, well, that should be a 3 there, plus 3. 216 plus 18 plus 3, that's 216 plus 21, that's 237, right, which is what we're after. So now let's go in and write down, let's move this again, shrink that down, and let's maybe circle an answer out of all this stuff too. So there's my answer for, or I can circle, this is my answer for converting our decimal number, our base 10 number, into a binary number or base 2 number. Remember, when you use the word decimal, we're referring to base 10. So a decimal number means a base 10. A binary number means a base 2. And so our base 10 number, also if you don't write a subscript, if you just say 237, we're going to assume that you're talking in the system that we're already familiar with. But let's just be clear and put a base 10 on that. So 237 in base 10. Let's see, there's 0 in here. We didn't have any dots in this box here. There are no dots, so we don't have to put that leading 0, but there's definitely a 1 here in this position. And now we can't skip zeros. If there is a 0 between filled boxes or partially filled boxes, you must have those zeros present. No boxes in the 36, right? That would like be insisting that you put a 0 in front of a 6 squared, just to stress that we're not skipping any powers of 6. 6 to the 0, 6 to the 1, 6 squared, 6 cubed. So it's really just the coefficients here, this 1, 0, 3, 3, that are going to become the base 6 number. So 1, 0, 3, 3, which is a base 6 number. All right, let's do hexadecimal. Hexadecimal is a counting system that is used, and it is confusing because we don't have single digit symbols for 10 or higher. Our single digit numbers are only 0 through 9. We could invent a new symbol for 10 that requires a single digit. Like maybe we could say that equals 10, and that equals 11. You know, you can make up new symbols for numbers that are, single digit symbols that represent numbers that are more than 9. But instead of inventing new symbols, what hexadecimal does is a base 16. So we need a total of 16 digits to be working with, 16 symbols. It uses the following symbols: 0, 1 through 9. So let's get the 9 up to there. So there's 10 symbols right there. And then it goes to the letters until we have a total of 16. Well, the A is the 10th position, so we have 10, 11, 12, 13, 14, 15. And we have 6 plus 10. Did I count that right? There's 10. Here's 6 more, so that's 16. So we get to stop there. Okay, so when you see the letter A, that stands for 10 of something. When you see the letter B, that stands for 11 of something. Right? Then 12, 13, 14, 15. We don't need a symbol for 16 because when you have 16 dots in a box, they will converge into a single dot in the box next to it. Okay, let's make a little rectangle and just see how many boxes we're going to need here. These are the ones, or the 16 to the first. The ones. Sorry, 16 to the 0 is the same thing as 1. Then we need, this box here represents how many 16s we have. And the next box is how many 16 16s. 16 16s is 256. This is 16 squared, in other words. And then we would have 16 cubed and 16 to the 4. So these boxes, they get pretty high pretty fast. And also I'm going to, so I only need 3 boxes. I'm going to do the following. I'm going to erase those middle lines. I'm going to give myself a little bit more space inside these, just in case we need to put lots of dots. and break this into 3. There we go. So there's how many 256s, how many 11s, and how many 1s. Okay, well, we don't actually even need any 256s, right? That's too many. You know, if I put a single dot in here, that means we're already at 256, and that's more than our 237. So we just don't even need, we don't need anything in that box at all. How about 16s? How many 16s? Well, 16 16s make 256, right? This is 16 16s. So I'm going to start removing 16 from 256 and see what we get. So 15 16s is take one more 16 away from 256, and that's 240. That's also too much. So we've got to go down to 14 16s, take another 16 away from 240, and that would give us 224. I'm just double checking. Okay, that's right. So we don't need, oops, I need to erase. We don't need that. So I need a total of, I need a symbol in here. I need 14 dots in here, I should say. So we need 14 dots. Let's go to put dots. 1, 2, 3. Let's make this ordered. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There they are. 14, and they're in the wrong box. They should be in that box. There we go. We have 14 16s. That gets me up to 224. Then how many more do I need to get to 237? I need 13 dots. And I'm going to put 13 dots in the ones position. Let's just copy paste and you remove one of them. There we go. And there's 13 dots in that position. So we just said that 14 16s plus 13 ones should give us the 237. However, we need to, let me shrink this down. I keep changing the sizes because I keep thinking I need to keep adjusting what I need to put where. Let's also write down over here 237 minus 224 is 13. That's how I knew how many singles I needed right here in this one position. Okay, so I need 14 and 13, except this is a 2-digit number. This is a 2-digit number. We're in hexadecimal. These are the symbols we use to represent these amounts. So I don't want to put it 13, 14. I want to go to my list here and say, hey, which symbol here represents the 14 position? Well, here's 9, 10, 11, 12, 13, 14. So an E represents 14 of something. And a D represents 13 of something. Keep in mind that all of our digits here, and there's 16 of them, need to be a single symbol. That's why we're not just putting 10, 11, 12, etc., because those are 2 digits for each. I need a single symbol when I'm in hexadecimal. So I don't want this 14 and 13 there. We have E14s, or E16s, which really means 14 16s, and D1s, which really means 13 ones, and that's how we get to this 237. So as a conclusion here, 237 in base 10 is the same thing as ED in base 16. Hopefully that hexadecimal is not too confusing when it introduces letters to represent amounts. It's something that it's worth wrestling with. It's a used base in our modern world, hexadecimal. Okay, let's move on now to this last question, part B. Express the base 5 number 143 in base 10. So in other words, we're saying, hey, 143, which is base 5 number, is equal to what in base 10? Is what we're after. So far, the only practice we have is going from base 10 to a different base, but now let's do the other direction, make sure we can do that. Also, notice that if I had given you 146 7 and said that this was a base 5 number, then you'd have a problem. Remember, base 5 means that you're only going to have 5 symbols or 5 possible digits. There's going to be 0, 1, 2, 3, 4, because 5 dots would merge into a single dot as you go from box to box. So there would be an inconsistency there if I said 147 was a base 5 number. All the digits have to be 4 or less if it's a base 5 number. Okay, well, the first, let's work right to left. The 3 represents how many 1s there are. Right, the 4 represents how many 5s there are, and the 1 represents how many 5 squares there are. We just do powers of 5. So you could read this as there's 1 5 squared plus 4 5s plus 3 1s, and do our traditional arithmetic on this to figure out what number we get. Well, that's 25 plus 20 plus 3. Well, that's 45 plus 3, we get 48. So that answers our question. 1, 4, 3 in base 5 is the same thing as 4, 8 in base 10. You could have also done this with the boxes, right? Something like this. This represents 1s, 5s, and 25s. And we have a single dot here. We have 4 dots in here. And we have 3 dots in here. You get the same idea here. This just translates into we have 125 plus 4 5s plus 3 1s. We get the same thing. Just using a visual instead. All right, that's counting in other bases. And this last slide is going to go pretty fast. It's just a quick overview of the history of other cultures and how they counted things. For example, the Romans have the Roman numeral system that you may be familiar with. We still kind of use it in today's society. Like if you watch the Super Bowl, they use Roman numerals there. And you'll see them here and there, Roman numerals. I don't want to say too much about this, but a single hash mark stands for 1, so that's 2, that's 3. When you the single symbol values are what's important here. The 1s, the 5s, the 10s, the 50, 100, 500, and 1,000. Right, so you have those 7 single digit values. And if you were to put a larger digit followed by a smaller digit, and then the implication is to add them. So that would mean 5 plus 1, you get to 6. But in this case here, when you put a smaller digit in front of a larger one, it means to do some subtraction. It means remove 1 from the 5, and that's how you get this 4. It's sort of a convention of doing the Roman numeral system. I'll let you ponder, all these other ones that you see in here and why those make sense. The Egyptian system here. Let's see if I remember what all these things stand for. The 1 was like a stick. It represents a stick. I think this was some sort of heel bone or something like that. This is for 10. This is a spiral sometimes. I think it's a rope, if I remember right. Then here we have, this is a flower. Sometimes you see in a pot with a little flower opening a certain direction. A lotus flower, I think, if I remember right, stands for 1,000. This is actually a finger and a fingernail on the top. It's kind of a creepy thing, someone's finger. This one's either a frog or a tadpole or something that looks like a fish, like it's kind of crawling like an amphibian. You see a variety of things. And this one here is sometimes called the surprised man, a person who is a person with their arms up. And they represent these different values. Here's an example of 4,000. So they do the 1,000 symbol, 4 of them. And then below that they put 6 ropes there, and each rope is 100. So this is 4,600. And then below that we see a couple of 10s followed by a couple of 1s. So 22. That's Egyptian. The Mayan system was pretty simple. I don't see the Mayan system being very useful for extremely large numbers because they just do 5s and 1s as their 2 basic symbols. Dots are 1s and 5s are bars. I've never really done any work with the Mayan system myself, but just pointing it out for you. And the Babylonian system is a base 60 system. This one's rather interesting. This symbol here, which I don't know what it is to be honest, stands for 1, and you just make more and more of them to get different numbers, and you kind of group them in rows of 3 until you get to 3 by 3, which is 9, and then you introduce a new symbol for 10. And then from there, they just put them side by side. So here's a 10 and a 1, so that makes 11, right, etc. Here's a 10 and 9, that's 19, and then you have 2 10s, etc., up until 59. I think they allow for 5 10s followed by 9 1s, and you get 59. You have 59 different symbols here. Granted, they're not single-digit symbols, but they are symbols that represent 1 through 59. This is the base 60s system. So if I were to do the following as an overall combined, let's grab, I think I can copy paste. Let's grab this symbol right here. Oops. Copy and paste that down here. Then I'm going to take this symbol right here. Put that there. And you want to put a little bit obvious of a space kind of in between. And then let's do maybe, we can do a simple symbol, or we can do one of these higher symbols. It doesn't matter. Let's just go to a simple symbol like this one right here. Let's copy that. Okay, so when you see these symbols side by side, recognize there's 3 groupings here. So you make this box here. This is how many 1s we're working with, and this is a base 60. So this is how many 60s we're working with, and this is how many 60 squares, which is 3,600. And then each of these symbols represented what? Well, this is 25. So we have 25 3,600s. This one's a 1 with a 9. This is 19. And then we have 19 60s added to that. And then this last one is just a total of 4. Am I counting that right? Yeah, 4. And then we have 4 1s. So when you see these symbols side by side like this, this is saying that we have the value in decimal. Oops, let me do this. The value in decimal. Oh boy, those didn't move with it. Struggling. Oh wow, okay. Not sure what's happening here. Let me just put that back. In decimal, this would be the representative of, we have 25 3,600s plus 19 60s plus 4 1s. So we're going to get a rather large number out of all this. I'll leave it to you to compute that, but it doesn't take many symbols side by side to get to very large numbers. You know, a base 60 counting system compounds fast as far as quantities are concerned. Okay, that's it for this week's material.